Welcome to Cafe Sci. And they asked me to talk about the Arctic, and they asked me to talk about the changing Arctic. Next week, Steve Baer is going to be talking about how we get the data that go and are behind what I will be talking today. And so both of us started probably with over 100 slides. Yeah, it's just, so the reason I say this is there is no way I can cover everything that I would like to share with you. And so it's your homework, and I've put some placeholders here. It's your homework to ask me the questions so that I can give you those answers to the extent that I can, okay? All right. So today, this is a photograph of what we call the Seasonal Izone or marginal izone. In other words, this would be in spring to summer, depending on where you are in latitude towards the north. And this one happens to be close to Spitsbergen because it's on the northern side, because you see land. And you normally don't see land in the Arctic. And so I will show you several pictures of what most of us are attracted to in the Arctic, okay? So we have territorial polar bears, large fish, which are result in large fisheries of various types, smaller fish on which large part of this Arctic food web is based, king crab, even though our lobsters, of course, are significantly better and better tasting. Whales of different types, large flocks of birds, and charismatic mammals that makes all of us, just like happened here, go, oh, yeah? Except that, what resources are the ones that fuel all of these large organisms, including humans? And those are, of course, charismatic microflora. This is what you come here to listen to, the Bigelow Cafe Sci, all of those microbes, always microbial, always phytoplankton, microbial food webs. In this case, it's a combination of both phytoplankton, which are microalgae, which are floating in the water, as well as what we call ice algae, which are living within the ice. Here, Dr. Apollonius, one of his favorites. What you see here is a variety of diatoms. These are stained. Some are chains. Some are individual pictures. This is a valvar view. And here you have them without stain. Again, more diatoms, as well as some other groups. This is Phaeocystis pauciti. Fish larvae don't like it, and zooplankton don't like it. And this is one that looks just like it, but it is also made of diatoms. So you see there is a large variety in the forms and in the shapes that these have. And so what do these need to grow? They need sun, light, just like plants on land, and that impinges on the ocean. Now, of course, if you will allow me, I will use this wonderful drink here as my metaphor for the ocean, and you'll see why. Okay? In this case, in the Arctic, it's got ice at the bottom. Yeah? It's stratified. In other words, it's got a couple layers. And the goodies that the plants need, the phytoplankton, are at the bottom, just like in this delightful drink. And so this ice and this, in the Arctic Ocean, fresh water, allow for this two-layered situation that prevents the nutrients which are below to mix into the surface. Okay? And so let's talk a little bit about where does this fresh water come from? Because this is the most obvious change in the Arctic right now. And so what you see here is ice decline. The first one, this graph here has time, years along the bottom, 1978 to last year, 2014. This is extend in millions of square kilometers. And you see a clear decline with a lot of variability. Even 2007 and 2012 are the two lowest years in ice extent in record. But then it bounces up. Now, it's hard to understand what this means, and hence I added this map here that shows the Arctic. Here is Canada, Alaska, this is Russia and the East Siberian Sea, Greenland, and this is Scandinavia over here. The yellow line indicates the average ice extent for September, which is the minimum for the last 30 years. This one happens to be the biggest minimum, 2012. And what you see is that it's very variable. It's not that it's melting or thawing in the same way everywhere. It is most on the side of the Pacific into the Siberian Sea. Now, it's not enough for the ice to appear and disappear. What's also changing is the thickness of the ice, and that is equivalent to age. And what you see here is, this is 2014, dark navy blue is open water, purple is first-year ice, white is multi-year thick ice. You see now, there's only a very narrow band in here. And I don't know how. I think I have to come over here to get this one. Because this is a short, very short, quick animation from 1981 to 2003 of the changes in ice. In this case, red is old, thick ice, and dark blue is first-year ice, with light blue being open water. What I want you to see is how fluid it is. This ice is moving all the time. So the concept that we normally have is that it's frozen and it's stuck. Some of it is, land-fast ice is, during the wintertime. But for the most part, the ice goes around, it moves, and it actually goes out as well. And there's a fourth thing that is very important when we talk about sea ice, and that's snow cover. Many of us who were here this winter, it was a cold winter, and that allowed the snow to stay. And because the snow stayed, the ground actually did not freeze as much, and oh dear, ticks did not die and fleas did not die because it wasn't cold enough underneath the snow. No different here. And so the snow acts as an insulator for the ice, keeping it cold and also preventing it from melting so much. Another source of water are rivers. And here you have the 6 major rivers, 2 on the North American side, 4 on the Russian side. These gray areas show all of the many small rivers which are around there. Each one of these blue names is a river, in such a way that there is fresh water going into the Arctic Ocean everywhere where there's this red line. That's all I'm trying to say here. And now, of course, there's also glacial melt going into there. And you see here, again, this is time. This is river discharge, in other words, fresh water. And it's increasing. The red line is for Eurasian rivers, the ones on this side. The blue line is for American rivers. So we have more fresh water going into the Arctic. And, oh, I love this picture. So I put it in here to show you that these rivers, this is the delta of the Colville River on the Canadian Arctic. They're very complex structures. I always tend to think about a river estuary like the Sheepscot or the Damascata. It's very simple. It's actually not even a delta per se, in the sense that it doesn't have islands. There's a total gradient of lakes and things, and so what it's also clear is that these rivers are not only bringing water, and I want you to remember this, but also bringing sediments, bringing dissolved organic matter and other things which have a terrestrial origin. That's all going into the Arctic Ocean as well. Okay? And so the result of this is a pool of fresh water in what we call the Beaufort Gyre. Again, this is Greenland, Scandinavia, Russia, Canada, and Alaska. this is the North Pacific coming in, this is the North Atlantic going in. This is salinity. How salty is the water? Red and yellow is salty, pink is fresh. This is at 20 meters. And I chose this one because this indicates that these waters are making it and staying within the water column. They're just not in the surface as runoff and going on. They're becoming incorporated into the circulation of the Arctic Ocean. So what's going to happen to all of this pool of fresh water? It warms the ice from underneath. It prevents the mixing with the colder waters from below. We don't know. We really don't know. There's a major study right now looking at the outflow right here going around Greenland, as well as waters that may be coming through the Canadian archipelago. And so, as I said earlier, in addition, there is, I didn't say it, I meant to say it. We have permafrost thaw. So the Arctic is an ocean surrounded by land. The Antarctic is different. And so most of the land is pouring into the Arctic. And one of the things, just like the water is warming, the land is also warming. And so this permafrost thaw is releasing some amount of groundwater. It's got to go somewhere. A lot of it goes into the rivers and forms part of the river flow. So I am not a hydrologist, but I want to know whether these groundwaters also carry nutrients and other things. So I asked a colleague who is a hydrologist and geologist, how much? And they go, we don't know. We haven't really measured it because it never was an issue before. It was frozen, so there was none. And so along with that, there is this enormous issue of coastal erosion all the way around the Arctic. As you can see, these are some of the villages and the communities. And this was not an issue before because since there was ice, the wind never developed enough fetch to create waves that would then erode the land. We're prepared for it. We know we see it around here. But there, it wasn't an issue. From an ecological perspective, this means that there is sediment that is going in that is going to affect the clarity and transparency of those coastal waters. And so I just said that when at the very beginning, since there is less ice, then it's likely to be more light. Now the sun can get through. Well, is that going to be the case in coastal waters? We don't know, but it is a very useful tracer to see these riverine waters coming into the Arctic. What you have here, all of these turquoisey and greenish and brownish waters are sediment-laden either river or groundwaters coming into the Arctic. These two are coming from the Canadian archipelago, the Beaufort Shelf, and this one is on the northern side of the Gulf of Alaska, in other words, underneath the armpit. To the extent that permafrost is thawing, anything that is in it will also come out. And one of the major ones is methane. And what will that do, in my case, to the food webs, because it fuels, in other places, a very large microbial bacterial system. So we have the sources of fresh water and to my top ocean. We have, unless I find a way of mixing the nutrients that come mostly from the Pacific waters to the surface, because they're at the bottom, I will have a low nutrient supply and hence not much productivity to harvest, because if I don't have phytoplankton productivity, I won't have zooplankton, I won't have fish, I won't have all of the marine mammals that depend on it. And there's already starting to see some of those things. And I talked about that. But I have one more hidden tool, if you wish, and that is wind. And I've used my straw here as a way of getting that energy into the bottom, right? So on Friday for the open house, there were some children there, and I were trying to come up with an analogy, and I said, do you blow bubbles in your drink or in your milk? Yeah? And I said it was in your soda. And then the child very seriously said, I don't drink sodas. Okay, I said, how about your milk? Same thing. So if I now, with less ice, I can effectively generate mixing. And what this cartoon does is now I have a lot more open water. Before it was closed. So now the wind can develop enough fetch to produce waves, to produce vertical mixing, to push the water aside and produce what's upwelling, because when you push the water aside, deeper water has to come in to fill the spaces which are there. And that's all what this means. I just want you to see that there is a lot more arrows and twirly-doos in this one than in this one when it's covered with ice. That's a major change for the Arctic. It's a change that we don't understand. We haven't been able to quantify. There are many of us out there right now with all kinds of fancy toys and tools, and you have to come back next week because Steve is going to tell you how you do those things to determine this. Does it only happen at the ice edge? Does it happen also under the ice? That's the big question. And so what does this mean, coming back to my phytoplankton? Okay? So what this cartoon shows is time from January to December, winter and the polar night. And then sometime in April, there's enough sunlight and heat to start melting the snow such that ice algae start to grow by June. The ice breaks up and opens and more light goes around into the ocean. Green means autotrophic production or plant production, and red means heterotrophic production or animal consumption. And what you see here is that I get about 2 green arrows. With less ice, the light is coming in earlier into the seasons, into the ocean. And so we end up with a longer growing period. But I still have the same amount of nutrients. It's not enough to have light. And so I will now end up with the same amount of harvestable production spread out over a longer period, which means I will have perhaps less over time. So if there is a mismatch between when this plant production is coming and when the animals are ready to consume it, we will have a problem. And hence, for years, the Arctic food web has been, for the most part, rather simple. And that's why you have a different cartoon. You have the ice algae and the phytoplankton bloom growing and then sinking with a very strong connection to what happens in the benthos, organisms which are in the sediment, with a large fraction of that water column or ice production falling to the bottom. And hence, a lot of these marine mammals that feed directly on those organisms at the bottom. And it has been, I was taught and still, that the Arctic is what they call a pelagic benthic environment. There's a lot of coupling between those two. With more open water now, the pelagic or the water column part of the system is dominating. And that implies that it will likely look a lot more like food webs and systems just right here in the Gulf of Maine, temperate waters, in which most of the action is happening in the surface layers and not getting down deep. That has lots of implications for diving mammals and for diving birds. And as well, the cycling of nutrients. So that's all that these two images indicate, that it's a lot more complex with many more actors than it used to be. And so, do we see this change? And we do. Do we see it everywhere in the Arctic? We don't. Do we have the data to support some of these trends? Well, sometimes. And so what I show you here is again time, 1978 to 2013. This is in the Barents Sea. This is annual production. And note that it goes from 60 to 130. So there's about a doubling over these 40 years. And with a stronger increase perhaps in the last 10 years. Now, the Barents Sea, half of it is open, always open water. It's not covered by ice. Okay. The graph on the left shows what appears to be a similar increase. But note that it only goes from 135 to 150. So if I were to plot it on the same scale, it would be utterly flat, no change, and perhaps even a decline. So if one summarizes this, these are all the various seas in the Arctic. And again, this is the trend in production. How much would it increase? And it's about 10%, except in the Greenland Sea, which is about 1% or no change, and some very high numbers in the East Siberian Sea and the Laptev Sea. Now, these are based on satellite data. This means that the satellite, it only extends for those years from which we have had satellite data. Does the satellite see the truth? Sometimes. Does the satellite get confused when there is ice in the water? Oh, yes. Does the satellite get confused when there is sediment in the water? Oh, yeah, absolutely. So we need data, field data, to validate these things. The two places where we don't have data to validate those are in these two seas of Russia. Maybe our Russian colleagues have the data, but they haven't shared. And so let's go back now to going up towards the food chain. And I'll show you here two model simulations that look at where this production has been. Please note, again, this is Russia, this is Norway, and Greenland. And so this is Svalbard, and this is our waters rich in production coming from the North Atlantic into the Barents Sea. This is the average of the previous 17 years, okay? It's high here in the Barents Sea, and blue is low pretty much everywhere else, except for in the Chukchi Sea coming in on the Pacific side. This is the same image I've just shown you. This is 100 years from now. This is a simulation, okay? All right, okay. So these blue circles indicate a slight decrease in production. The red ones indicate an increase in production all the way around, okay? So put in a different way, I have now zoomed just in this region here, okay? Just here. We now have Norway, and Russia. And you'll see why I'm making an emphasis on this. This is 50 years from now and 100 years from now. And the red arrows are going to indicate increases. Okay? So it's increasing towards the east. The blue arrows indicate decreases. And it's decreasing towards the west and towards the south. Something is going to be eating this. Most likely fish. The one fish that we have in common with them is cod, for example. Okay? So these are the cod that the Icelandic fish. These are the cod that the Spaniards fish. These are the cods that the Norwegians fish. Who's going to be fishing them in 50 to 100 years? Well, those are my fish. You don't get to fish them. So this is now translating into very serious issues about policy, about finances, about security, that go beyond my charismatic microalgae. Okay? That's one of the things that I wanted to show you. I had another message, but I knew this was going to happen because I know I talk a lot. And so this is your homework. I'm going to tell you these things are important, and you're going to have to ask me why. Okay? And this is the issue of teleconnections. The Arctic is not isolated from the rest of the planet. And then there is connectivity there from the perspective of weather, polar vortex and Arctic Oscillation. If I hear the Met person tell me one more time about the polar vortex, okay, I'll be 6, right? And the jet stream, oh my God, we're all going to die. But there is connectivity, and there's an enormous amount of discussion about the connectivity with local weather. With extreme weather, this is the storm in New Jersey. There are also questions about flow of fresh water coming around Greenland and through the Labrador Sea, and how much that is getting into the Gulf of Maine, and perhaps being responsible for the large amounts of fresh water which are being seen in the Gulf of Maine. Some of that is river. There was an article in the Portland Press Herald today or yesterday about changes in the lobster fishery. Okay? These are dynamic areas of research. Okay? I don't have time, but you can ask me to talk about shipping issues to the extent that there is less ice. I use here the example of 2 Canadian Coast Guards, because that's security. It's also fisheries. But it's very important issues about shipping. There is enormous increase in tourist shipping. There are issues about mineral exploration, resources, oil, gas, many different things. But we must not forget is that the Arctic has people. It has had people for thousands of years. It's not for us just because all of a sudden we are interested in the Arctic to just go there and decide how it needs to be done, how it needs to get managed. They've lived there. They continue to live there. For them, maybe these things are a bonanza, or maybe not, because it is really affecting their culture, how they do things, because these guys don't respect when they are in their very small canoes. And so it's very interesting. They talk a lot about resilience. They say the Arctic Ocean is always changing. It has always been changing. We've always gotten used to, we have to adapt. And so the last one I brought here is the Arctic Council. The Arctic Council is a governmental organization formed by the 5 Arctic nations. That's geographically Canada, the US, Russia, Norway, and Denmark because of Greenland. And the US has the chairmanship of the Arctic Council for the next 2 years. And there will be about 5 or 6 meetings, and 2 of them will be in Portland. We worked hard to get those in Portland. And so I urge you to be aware, to notice, and then contact. Our Senator King is very involved in that part. And with that, I'll be happy to take any questions. Thank you very much. I'm going to leave a little movie going behind, just so that you can see. At least I hope it works.
While Patty tries to get her movie running, she was instrumental in getting the Arctic Council to meet in Portland, so 3 cheers to her.
So this is just background. No, just keep it there. There's, again, impossible for me to share so many things. So I figured somebody else made this movie in Sweden, and that I would just leave it in the background.
And where is this?
I'm sorry, this is at 88 North. So it's way up there. So it doesn't really matter where you are because you could just go around and you'd be everywhere, just about, no? So I was, what you see, this is the Swedish icebreaker Odin, which you will see, in the back. And there's all kinds of things that they're doing. Yes, ma'am.
I'm curious about whether the sea creatures are adapting to the change. You basically talked about how as the ice cover, the snow cover disappears, and now we have a longer season for the phytoplankton, et cetera, that there's increased productivity, but over a longer period of time. It doesn't really necessarily coincide with the feeding cycle of the sea mammals, et cetera. So are you studying, or is anybody studying how they're adapting to that?
So the question is have we already seen adaptation in various organisms to this change? And so we see tidbits, because in order to see, one thing is acclimation, where you get used to it. Adaptation, you really change your ways. For that, it takes many more years than what we've seen up to now. What we see, both, for example, at the phytoplankton level, at terrestrial organism levels, we see movement of subarctic species coming in. So there are new species of phytoplankton moving in. There are new species of birds, or they're just moving further north or staying longer. No different than what we see even here in Maine. Stuff coming from that used to be only in Connecticut, but now it's all the way up here. You also see differences in migration. You see polar bears coming onto land. There are descriptions, anecdotal ones, of light brown bears. In other words, polar bears and brown bears and blacks actually mate. They are a species, but they do mate. And so they're seeing descendants. The question is, will those be viable? In other words, will they be on their herds, be able to reproduce? You see a change. The Arctic is greening, not just in the ocean, but also on land. But what's changing is a movement of shrubs and trees northward. But those beautiful, gorgeous, elks, large things of deer and all of those things that we see, those eat grass. They don't eat shrubs and trees. So what it means for that, it's too soon to say. It's too soon to say. Yes, sir?
What's the Arctic and the Antarctic contribution to sea level rise?
So what's the contribution of the Arctic and the Antarctic to sea level rise? In the Arctic, the major contribution comes from the melting of the glaciers, the land glaciers on Greenland. Okay? Compared size-wise to the mass of the Antarctic, those glaciers in the Antarctic is much, much more. It's much, much bigger than what's in Greenland. What is happening, though, is that the melting of the glaciers in Greenland is faster than those in the Antarctic, as the Antarctic is melting in a very uneven way. It's only the western side of the peninsula which those glaciers are melting. But on the other side, the Weddell Sea and other places, it's actually growing. Now, sea ice in the Arctic will make a difference. But sea ice in the Antarctic is a very small fraction of the ice. And in there, it's only annual. In other words, it melts and forms every year. The Arctic is getting to be that way because the multi-year ice, it's only that right there close to Canada. To the extent that it all becomes first or annual ice, then we will see it melt and freeze every year. Yes, sir?
A three-part question, interrelated. One is the Arctic Council. How is that constituted? Is this largely political, or is it also include
Okay, all right. Okay, Arctic Council, how is it made? What does it consider? And does it have any scientific input? So the Arctic Council is strictly governmental. So it is political, absolutely. They're all political nominees. There are 5 members, and then there's so much interest in the Arctic that there is now several nations which have applied and obtained status as observers. Several European nations, China, Japan, Korea, India is the latest one to apply. You see? And so to that extent, what is discussed there? Everything. From shipping to extraction to native communities. The position that our president has taken is that without science, we won't really be able to make informed decisions. So he is really pushing science into this. Going to Senator King, who was instrumental with Senator Mikulski in, did I get it right? In Alaska, in promoting not only the Arctic Council, but I can't remember, something like a US version of it to address some of these issues in Congress. Yes, you had a question.
You mentioned shipping in the Arctic. There's the Northwest Passage and then the northern route. Can you just talk about those a little bit?
So the question is, what's the Northwest Passage and the northern route? These are 2 of several possible routes across the Arctic. If one could ship through the Arctic, it's a lot faster and shorter than going through the Panama Canal. Yeah. And so the northern route is already open and is already being used. And it goes along Siberia. Yeah. And so that one is already the Koreans use it, sometimes with Russian icebreakers, escorts, or something like that, but they use it. A lot? No, it's still difficult. The Northwest Passage goes through the Canadian archipelago, so it's closer to us. It's significantly shorter because it goes along Alaska and then Canada, and then cuts across north of Hudson Bay. And that one, as you know, it's a treacherous one because it still has a fair amount of ice. Sometimes it opens for a little bit, but you got to time it right. Okay? Having said that, there are places like the Nares Passage, which was just to the end where the Davis and Labrador Current comes to there, which was always just a big plug of ice. And that now one is open, seasonally, sometimes. So it's getting there. I don't know. But people are watching. Yes, ma'am.
How deep would the passage be? In other words, how big could ships be that could get through?
The northern route, lots of ships of lots of things, to the extent especially if you don't go onto the shelves into territorial waters. The Northwest Passage, I'd say pretty deep.
That's pretty deep.
Yeah, pretty deep. Somebody, yes?
I've heard that because ice is more reflective to infrared than the seawater, that as we're losing ice and there's more seawater absorbing more infrared, it sort of becomes self-reinforcing. And I was wondering, for people in the field, is this considered already a runaway problem that can't be stopped, or is it something that might not just continue and accelerate?
So the question is, one has to do with what we call ice albedo, right? And so if you have a white car, it will reflect heat a lot more than if you have a black car. No, I came here from Miami. You would never have a black car there. Here you might want to have a black car because it's nice to get inside if it's really warm. The ocean is, from this perspective of radiation, it's considered a black body, so it absorbs heat. The more that it's open without ice, the more of that heat it will absorb and retain. And so the question is will the Arctic be devoid of ice all the time? Then, okay, we're done. Yeah? As we know the Arctic now, it will change into something else. To what extent do we get a lot of first-year ice? because every fall it freezes. How long does that first year ice last? If it's covered with snow, then it will last longer. But we're already seeing that the ice also lasts less time. Snow is a big issue. Snow on land and snow on sea ice. And if there is more water, even if it's cold, there ought to be more evaporation, and hence you ought to have more precipitation, more rain and more snow. Well, some people tell me that there is more snow, and some people say that there is less snow. That's a big question as well. We're getting there. Runaway, but it's getting close. It's getting close. Somebody else had a question. Yes, Chris.
Are there different types of plankton coming down the freshwater rivers into the ocean? And do they die when they get to the salt water? Do they coexist? Or are they basically the same creatures?
So the question is as to whether the phytoplankton that comes down the rivers, can they survive in seawater? And most of them can't. It's similar to what happens to the extent that you are in the tidal part of the river. It'll be estuarine, and some will survive there. And so you will have some marine and some fresh water that can tolerate some salinity. But the real fresh water are not going to make it, nor will the marine ones really make it all the way up. Yeah? The change that we're seeing main is that which is coming from the subarctic, which are marine species coming up, both on the North Atlantic through Fram Strait and in the Pacific side.
And what kind of plankton is actually frozen in the ice? Well, I mean, would that be marine plankton or freshwater?
So the question is, what kinds of plankton are what we consider ice algae? And those are mostly marine. They go the other way because now they have to be able to withstand extremely high salinities, because everybody here makes ice, right? In the refrigerator. Have you ever tried to make frozen ice? I mean, salty ice or colored ice? Try it. No, it's an experiment. It does not end up being salty because when it freezes, the water rejects the salt. It also rejects all kinds of other things in there. It doesn't reject it proportionally. But you end up with the salts on the outside of the ice. And the ice itself, the older it gets, the fresher it is. Except that it has pockets. Yeah? The ice has pockets. It's not a solid brick. And in those pockets, the salts concentrate. We call that brine. And so to the extent that you end up as a microalgae inside those, you have to coat yourself with something. And a lot of them are coated with some type of mucus. Most of them are diatoms. The majority of the microalgae, the ice algae, are diatoms. There's a few others, but they're mostly diatoms. I'll take somebody from the back. Yeah. So I said that the nutrients in the surface waters are low. They're not necessary, no, and hence that unless you can increase them some way, they will remain low and hence control how much production you can have. The main source of nutrients is coming from below. It's Pacific nutrient-rich water that comes from the North Pacific and tends to sink. You need to somehow mix that up to the surface. The rivers do bring some nutrients, but the experts tell me that compared to the nutrients which are available in deeper waters, it's not as much. It may be very important in coastal regions. And so if we try to understand what's happening right there on the coast, where people live, where a lot of these activities that I'm talking about, fishing, tourism, exploration, a lot of that is in the coastal regions. Then we need to understand that. Yeah? Oh, sorry, I'm moving back in front to back.
How will these changes affect the deep ocean circulation?
So how do these changes affect the deep ocean circulation? That's a big question right now. The main difficulty to answer that question is how do you sample that deep ocean when it's covered with ice? There's still ice there. So it means that you depend on icebreakers and have in the past depended on icebreakers to get there. Unless you develop some sort of autonomous, automated system that you can deploy on the ice that will just simply stay there and survive the harsh winter conditions. And several of us have been working really hard on that. Physical oceanographers in Woods Hole have something called the Ice Tether Profiler. Just hangs on the ice, and it does profiles down to 1,000 meters once a day. People at the Naval Postgraduate School have what they call the flex buoy. It's measuring energy and all of that. Others are, Corel has ice mass balance buoys. And of course, I was presented with this situation, can't get there, and so we decided we needed to one that looked at air quality as well as some biological properties. And so some of you have put up with me before talking about what I call buoys. Again, a similar system collects data and analyzes the air right there and then transmits the data via iridium to my office where I look at it. What those data are showing is that the Pacific water that comes in through the Chukchi Sea and goes down in depth is actually making it all the way around into on the Atlantic side. The Arctic circulation has two modes. One in which the larger flow, the dominant flow, is the flow that comes through the North Atlantic. Some of it goes through Fram Strait just into the Arctic. Some of it goes around into the Bering Sea on the Russian side and then pours into. That's the dominant flow. It goes a lot further. At times, and it's called the Arctic Oscillation, some of the North Pacific water comes in further east, I guess it would be. So those two stages go back and forth. Probably the newest thing is what they call these eddies. And we did not know, but these seem to happen all over the Arctic. And so instead of having a current that just flows like an unavoidable stream of thing, there are these little loops, circles that are maybe 100 kilometers in diameter, and then they trap water, and then they move underneath the ice. How are those transporting these properties? Is a very active field right now. And how much of that water then will make it out into the North Atlantic? Almost none of these waters make it out into the North Pacific. That's not it. It all empties out through the Canadian Arctic and the North Atlantic.
So it's not sinking and moving down toward the equator.
You've gone. I'm just staying within the Arctic, okay? Oh, yeah. Okay. That's a bigger question. So she asked, is this that water's getting into the North Atlantic? So our understanding of the circulation is that the warm water of the Gulf Stream goes through Cape Hatteras and then turns east and goes by England. That's why England has palm trees when we don't, because they have all that nice warm water. And it gets about somewhere between England and Norway. It gets now cold enough. It's now dense enough, and it sinks. And it goes then all the way down, back down to in the North Atlantic, but down at depth, sort of on the western side, and it just goes all the way around. That's what we call the conveyor belt. If those waters are not able to get so far north, because you have fresh water that is coming, let's say the top 200 meters or 1,000 meters. Don't quote me on this, okay? Don't get me in trouble. Such that they form a barrier and these are not getting, then we will have less of these salty, dense waters going in. It's highly unlikely that the Arctic waters will ever make it down deep because they're too light, they're too fresh. Yeah? And so even if they're cold, they're just too fresh, and so they will glide on top. So the question is, those will be coming in the surface. How far south will they get? Will they get all the way south of Greenland, go all the way around the Labrador, and perhaps into the Gulf of Maine? as you come through? That's a big question. Don't have the answer for that. So yep. So the question is, no, the comment is that I have now shown that it is a very complex system that requires lots of different variables and lots of different data to be taken. I want to make the point that we've sampled the Arctic mostly in the summertime because that's when we could get there. But we now realize that it's actually, stuff is happening year-round. So we also need to sample in the wintertime when it was supposed to be, well, it is cold and dark, but it was supposed to be dead, and it's not. And so I had one slide, and I took it out. And the slide that I had is a slide of the various Earth system models, the big ones that capture the entire planet. How well are they capturing the Arctic? Can they reproduce ice change? Can they reproduce vertical mixing? Very simple, just the top 100 meters. Can they reproduce the amount of nitrate as an example of one nutrient in those surface waters? And hence, if they've got all of their mechanisms and all the process coded in the right way, can they give the right amount of prime production? And the answer is very simple, no. So the variability, the envelope, so what it was, the figure shows a black line, which is the data, and then an envelope, which is orders of magnitude on either side of that line, which is the result of these simulations. So the question becomes then, how do we improve them? Should we go to perhaps smaller regional models, which can have more details for the Arctic? That's one. Should we go to what they call higher resolution? Because these Earth system models, their basic units is like 50 miles by 50 miles. Can do lots of things. 100 kilometers. That's huge. I mean, my phytoplankton, everything that I've shown you in variability, it's on the kilometer scale. So we need to do that. And there are, and so I currently, because I argue with the modelers, they say, oh, Patty, you don't like models, and oh, Patty, you don't like remote sensing. And I said, it's not that. We just simply need to understand the limitations of any tool that we have. What can it do? How much can it do? How much it cannot do? And so I have a project specific for the Arctic Ocean primary production, comparing these models. We just had a paper accepted comparing what we call ocean color models. These are models like the one I showed here that use remote sensing. The next step are general circulation models. And we send the data to folks, and then they plug it into their model, send us the result, and we just compare it to the data. The goal, this is not a beauty pageant for models. It's not that yours is the best and yours is out to lunch. That's not it. It's what can we learn that the model that seems to simulate better has that should be incorporated into the others? Because we all want to get it right or better or closer to it. So there's a lot of work being done on that as well. The Arctic is not simple as the temperate and tropical oceanographers are discovering. Yes?
Can I mention one thing about the methane, which you mentioned coming out of the Alaskan permafrost? And it's a very scary thing. I think there's permafrost not just in Alaska, but all around the basin. And you can repeat this.
No, you can say it.
There's permafrost not just in Alaska, but all over the Arctic, around the Arctic basin. And it contains an awful lot of methane. And that methane is coming out. And the scary part is that methane is between, 10 and 20 times as potent as carbon dioxide on climate change.
So, this question about methane, and I must say that one of Bigelow Research, senior research scientist Beth Orcutt, is right now in the Arctic looking at emissions of methane from lakes. There's lots of lakes in the Arctic. And so, April, I saw a fabulous talk from a Norwegian geologist looking at methane in the Arctic. And they now have tools with which they can actually see the bubbles of methane going up, and hence measure, if you can somehow measure the gas inside the bubbles and estimate the size and diameter and the frequency of those bubbles, you could actually get pretty good estimates of how much is coming out. And so the question is, how much of that will get to the surface? To the extent that it stays at depth, pressure keeps methane frozen. So they had this fabulous picture of the bubble of methane coming just out of the sediment and then just becoming a frozen ball. And then they captured this, and then as they brought it, they had a camera inside this thing, and as they brought it up and pressure decreased, then all of a sudden this frozen ball just disappeared, and clearly it dissolves into the water. Now, we need to get those waters to the surface to exchange with the atmosphere in order to get that methane into the air. And so it's risky. We haven't seen yet, we haven't measured yet, increased flux of methane into the air. Okay? But clearly it is coming into the lower, bottom waters and out of the sediments. How much? Don't know. They just, lots of people, geologists, geochemists, and microbial types looking into that right now. Yes, sir?
Now that you mentioned that, you need to mention clathrates, which are a frozen layer of ice along the continental margins. And if the water warms it up, if that stuff's melted, we're going to be in serious trouble.
You mean methane clathrates?
Yes.
Yeah. And so that's, the permafrost. So the question is about methane coastal regions, which is frozen. And so most of the methane is in the sediment, in the permafrost. But there is permafrost that goes all the way down into the ocean, the sediments there, in the coastal regions. And that's effectively what that seminar was all about. And that's the big question. How much of that will stay frozen now, because pressure keeps it there at that. The one on land is now much more exposed, and that's what we're seeing. But there isn't as much on land as there are in these coastal deposits.
We have time for one more question if somebody has it. Otherwise, we'll thank Patty. So, any hands? Thank you very much.